Okay, here we go with Chapter 2. Number 1. Terry is skiing down a steep hill. Terry's elevation, E of t, in feet after t seconds is given by E of t equals 3,000 minus 70t. Write a complete sentence describing Terry's starting elevation and how it is changing over time. Well, I'll let you write the sentence, but I'll explain what they're talking about and go over how you would write this. Now, Terry's starting elevation would be when t equals 0. That's before he actually, well, when he's on top of the mountain or the hill, and that's when the time equals 0. So E of 0, that would be his starting elevation. Just let t equal 0 in that function E of t, and you get 3,000. And we're talking about feet here. Now the change, how it changes over time, the change is given by the slope. If you notice, this function is written in slope-intercept form. It's a straight line, and the slope is next to the variable t, and it's negative 70. So the negative implies we're losing altitude over time. Alright, so the slope is negative 70, and it's in feet per second because those are the units we're using. So that means that Terry is descending at 70 feet per second. Number 3. Jessica is walking home from a friend's house. After 2 minutes, she is 1.4 miles from home. 12 minutes after leaving, she is 0.9 miles from home. What is her rate in miles per hour? Alright, well, if you remember the formula, distance, rate, and time. Distance equals rate times time, so r equals d over t, alright? So in this case, her rate is going to be the change in d over the change in t, or delta d over delta t, where delta represents change in. And that's 1.4 minus 0.9 miles over 12 minus 2 minutes. And that equals 0.5 over 10. That's 0.5 miles over 10 minutes. And that equals 1/20th miles per minute. Alright, because the units we're dealing with in the statement of the problem are in miles and in minutes. Alright, so miles per hour is what we want, though. So we're almost done. What we have to do is convert this to miles per hour. And so there's an easy way to do this. And I hope you've seen this before. Okay. So 1/20th miles per minute, I want to change that to miles per hour. What I do is I want to cancel the minutes out here and somehow get hours in there. Alright? So to do that, you multiply by 1. Why 1? Because you don't want to change this value, right? You don't want to alter it. Well, you don't want to change it, but you do want to change it or alter it so that you have miles per hour. Well, what I want to do is cancel the minutes, so I write a fraction representing 1 here, and I put minutes in the numerators. Minutes in the numerator so I can cancel the minutes out. Now, what I want down below is hours, 1 hour, or just hour. All right. What's an hour? Well, it's 60 minutes. So the numerator equals the denominator on this fraction, meaning that it's equivalent to 1. So you're not changing the original fraction. All right. So what this accomplishes is the minutes cancels out. All right. And what you end up with is miles over hours, or miles per hour. Okay. Now, what you have here, this is all being multiplied together. Think of that as multiplying there. Okay. So 60 over 20, that would be 3. So we've got 3 miles per hour. Miles per hour. All right. This kind of conversion that I just did is usable in many different contexts. I recently wrote a book of test sample questions for nursing. People who want to study to be nurses, they have to go through these tests, and I did the math portion. This book had a lot of sample math test questions. And there's a lot of problems where you have to convert between different units. And this is a very important skill because if a patient needs a certain amount of drug and it's in one unit and you need to convert it to another unit, it's critical that you do it correctly because you may overdose the patient otherwise or not give the patient enough. And so, it could be dangerous for the patient. So, if you're planning to get into those kind of fields, get used to this technique. It's very effective, and you'll be required to use it probably later on, especially if you're into nursing. All right. Anyway, that's our answer: 3 miles per hour. Number 5. A boat is 100 miles away from the marina, sailing directly toward it at 10 miles per hour. Write an equation for the distance of the boat from the marina after T hours. Okay, so it's a constant speed. The boat's going at a constant speed of 10 miles per hour, and it starts at 100 miles away. Okay, so since it's going at a constant speed, we can use a simple linear equation, and we are in the section dealing with linear equations, aren't we? So we expected that, didn't we? So, but it's going at a constant speed, so we can use that as part of the equation, and it's going to be linear. So d is what we need. Distance is equal to, it's going to involve t for time, and when t equals 0, that means the boat is 100 miles away from the marina. That's the starting point, right? And it's going toward the marina. So as time increases, we're expecting the distance to decrease. We wanted to start at 100 miles. So when t equals 0, the equation should give us 100. And if you think about it a little bit, after 10 hours, and it's going at 10 miles an hour, right? After 10 hours, the boat will hit the marina. All right, it will have gone 100 miles. So we should get an answer or a distance of 0 at t equals 10. Okay, so that'll help you set this equation up. All right, it's going to be 100 minus 10t. Okay, so when t equals 0, d equals 100. When t equals 10, this is going to be 100 minus 10 times 10 is 100, or 0, which is what we expect. And we can also put a domain restriction on this. The book doesn't really bring this out in the answer, but you can do this. T has to be between 0 and 10 hours, right? Anything after 10 hours really doesn't make sense in the context of this problem. Anything less than 0 also doesn't really make sense in the context of this problem. Okay, the way it's stated. So, there you go. Number 7. For the following exercises, determine whether the equation of the curve can be written as a linear function. And what we have here is y equals 1/4 x plus 6. First of all, you need to know what a linear function is, all right? So we have an idea as to what we're supposed to do here. A linear function. What's that? It has to fit into this format. Some function f of x equals mx plus b. Remember, y equals mx plus b, that's the slope-intercept form of a line. Same idea here. Alright, traditionally we use m to be the constant next to the x. I mean, you could call it ax plus b if you wanted to. If you take statistics, they'll use different variables, but it's basically the same. It's a straight line. They'll use different variables for m and b sometimes, you know, so it doesn't matter really what you choose, but it's got to fit that format. The variable is right there, okay, the x. You can also use different values or different letters for x as well. Traditionally, variables use the letters at the end of the alphabet, and constants use letters toward the beginning of the alphabet. Okay, so m and b are constants. So m, b, or just real numbers. Okay, so that's a linear function. Can this be written as a linear function? Well, it's practically all there for us. Alright, yeah, it's written that way for us already, just about. You can call it f of x if you want to, instead of y, or g of x, whatever you want to call it. So there's your m is 1/4, the b is 6. Alright, so the answer is yes. Okay, number 9. Y equals 3x squared minus 2, which I've written already. Alright, so can we write this as a linear function? Well, if you look at the format, the power on the x, the exponent, has to be 1. Y equals mx plus b, alright? Here the power is 2. Although we do have the two constants, m and b, if you want to think of those as being m and b, alright, m is 3, b is -2, but the power on the x doesn't fit that of a linear function, okay? And a linear function will have the graph of a straight line always. But this has a parabola as its graph. Okay, you remember those? So if you graph that, you'll get a parabola, which is not a straight line. So the answer is no. Okay, you could, over here, you could have m equals 0. There's no restriction on m and b, so m could equal 0, and then you would just have f of x equals b. So b could be any constant, all right? So y equals 7, for example. That's a horizontal line. Anyway, all of these functions where m is 0 will be a horizontal line going through y equals b, whatever b is, okay? So both of those could be 0. M and b could both be 0, so you'd have y equals 0, or f of x equals 0, which would be just, basically it's the x-axis, all right? That's going through y equals 0, horizontal line, all right? But on linear functions, the degree of x, or the power on x, always has to fit this format, which is 1. The power will be 1, okay? So again, the answer is no on this one. Okay, number 11. 3x squared plus 5y equals 15. Alright, well, again, the power on x here, let me write this down. 3x squared plus 5y equals 15. You could isolate the y, get everything to the other side, and multiply both sides by 1/5 to get rid of that 5 there, and kind of get it into this form, but still it's not going to be linear because the power on the x is not 1, it's 2, so what you have here is a parabola, alright? So this is not a straight line, and it's not a linear function. Number 13. Negative 2x squared plus 3y squared equals 6. Alright. Well, again, the power on the 2 is not what we're looking for. We're looking for a power of 1. So this isn't a linear function. What is it? Well, you can isolate the y on this. Take the square root of both sides. And don't forget you have a positive and a negative square root. So you're going to have y equals plus or minus the square root of so-and-so. Okay, whatever it turns out to be. And you can graph both of those on your graphing calculator and see what the result is. Alright, but it's definitely not a straight line. Alright, okay. Number 15. For the following exercises, determine whether each function is increasing or decreasing. Well, what you do is you note that these are linear functions. Look at the slope, and if it's a positive number, then it's increasing, and if it's a negative number, then it's decreasing. All right, it's just that simple. So we have f of x equals 4x plus 3. The slope is the number next to the x, and that's a 4, it's positive, so that means it's increasing. Number 17. A of x is 5 minus 2x. Again, the slope is the number which is next to the variable here, and that's a negative 2. Alright? Since it's negative, it's decreasing. decreasing. Okay, number 19, we have h of x equals negative 2x plus 4. So the slope is next to the variable there, x. So the slope is negative 2, which means that it's decreasing. It's a negative slope. Decreasing. Number 21. J of x is one half x minus 3. So the slope is 1/2. Positive, so it's increasing. Number 23. N of x is negative 1/3 x minus 2. So the slope is a negative 1/3. Negative meaning it's decreasing. Number 25. For the following exercises, find the slope of the line that passes through the two given points. So you've got 2 points, and you can use the formula for slope. Remember that, that's y2 minus y1 over x2 minus x1. Alright, so we've got the points 2, 4, and 4, 10. Okay, now it doesn't matter what you call x1, y1 and x2, y2. Alright, you can call this x1, y1 or this x1, y1 because, well, it doesn't matter. You'll get the same result either way. If you don't believe it, try it both ways and you'll see. If you don't make any mistakes in your math, that is. Alright, just don't mix up the subscripts in one point, like don't call that x1, y2 or something like that, okay? Keep the subscripts the same for each point. x1, y1 or x2, y2, either way, alright? Okay, so let me write down the formula. Slope m is y2 minus y1 over x2 minus x1. And I'll just go in numerical order here. Call that x1, y1, x2, y2. Alright, so you've got 10 minus 4. So that's y2, which is the y-coordinate here, y2, minus y1, which is that y-coordinate there, over x2, this is x2 here, 4, minus, and that's x1 there, alright, 4 minus 2. So that equals 6 over 2, which is 3. So that's the slope of the line joining those 2 points. Number 27. We have the points negative 1, 4 and 5, 2. So let's let this be x1, y1 and that be x2, y2. Alright, so we've got slope m is y2 minus y1 over x2 minus x1. So that's 2 minus 4. There's y2 minus y1. 2 minus 4. And then x2 is 5 minus x1 is negative 1. So you got 5 minus a negative 1. So I'm putting the negative 1 in parentheses so I don't have two minus signs butting up to each other. You know, we've got to keep things organized here. So 2 minus 4 is negative 2. And 5 minus a negative 1 is equal to 5 plus 1, which is 6. Alright? And that's equal to negative 1/3 reduced. Number 29. We have 611 and negative 4/3. Again, I'll just call that x1, y1, and that's x2, y2. Alright? So slope m is y2 minus y1 over x2 minus x1. And that's equal to 3 minus 11, that's y2 minus y1, over x2, which is negative 4, minus x1, which is 6. Alright, so that's equal to negative 8 over negative 10. Negative divided by negative is positive, so you're going to get a positive answer, and reducing that, you get 4/5. Number 31. For the following exercises, given each set of information, find a linear equation satisfying the conditions if possible. Okay, so here are the conditions. F of negative 1 equals 4, and f of 5 equals 1. Alright, so in other words, when x equals negative 1, y equals 4, and when x equals 5, y equals 1. So we have 2 points here, negative 1, 4, and 5, 1. Which means we can use the slope-intercept equation, or the point-slope equation rather, and get the slope, or we could put it all in one equation, right? You have y minus y1, there's the point slope, equals the slope m times the quantity x minus x1. Alright. M is y2 minus y1 over x2 minus x1, so you could put that in there, right in this equation, and so it's all there for you. You don't have to do the slope separately, just put it in the point-slope equation. I've heard this called the two-point equation. We have 2 points here, x1, y1, and x2, y2, which go into this equation. All right, hence the name two-point equation. Okay, so we'll plug in our points here. And again, it doesn't matter which ones you call, which point you call x1, y1 or x2, y2. All right, you can call that x1, y1 if you wish, or this one, x1, y1. again, don't mix up the subscripts, all right? Don't call this x1, y2 and x2, y1, all right? That'll really mess you up. But if you choose either point as x1, y1 and the other one is x2, y2, you'll get the same results no matter what. All right, the computations will look different, but you'll get the same result. So anyway, here we go. This is x1, y1. So you got y minus 4 equals y2, that would be here. 1 minus y1, that's 4. Over x2, that's 5 minus a negative 1. Parentheses, x minus, and then x1 is negative 1. Alright, so there we go. So I'll deal with this minus 4 later. Let me do this part first. 1 minus 4 is negative 3. This becomes 5 plus 1. Minus a negative is plus. So 5 plus 1 is 6. And then you've got x minus a negative 1 is x plus 1. Okay. This, of course, is negative 1/2. So I'll distribute the negative 1/2 through. Negative 1/2 x. And then negative 1/2. Alright. Now, you move this negative 4 to the other side, alright, or add 4 to both sides. Negative 1/2 x minus 1/2 plus 4. Alright. Let's see, we'll move it up here. So we've got y equals negative 1/2 x. And 4 has to have a common denominator with 1/2 or negative 1/2, and so 4 is the same as 8 over 2, right? Or you can multiply 4 by 2 over 2, which equals 1. 4 times 1 is still 4, but if you make that 2 over 2, it'll be 8 over 2. 4 times 2 over 2 is 8 over 2. So it's plus, rather minus 1/2 plus 8 over 2. Alright, so that's negative 1/2 x. And then you can add the numerators here. 8 minus 1 is 7, so that's 7 over 2. Alright, so y equals negative 1/2 x plus 7/2. That's our answer. That's the equation of the line that goes through these 2 points. Or if you call this f of x instead of y, and you plug in these x values, you'll get these y values as a result.